previous number, but in the new curriculum it's MEL 7423. So I think you are MEL 7423. And this has got 3 lectures, Tuesday, Wednesday, Friday, 10 to 10:50 in this room, LH 603. And we will have 2 hours of practical, okay, because this course is 302. Now, this we have to decide the actual hours of the practical. We will have to decide once other students join, because just discussing with the two of you, probably you will not be able to decide the timing. Okay, so 302, and this 2 hours, even though it's we say it's practical, but you will not be doing experiments. Okay, but you will be doing some design calculations. Okay. So like for example, in undergraduate you have machine design, isn't it? So you let's say you are designing a gearbox, then there are some formula, there are some assumptions that you make. You start with the calculations, you make a gearbox, and then maybe you're not happy with that design, and then you change the design, things like that, iterative process, right? So this is something similar to what we will do in this course also. So we'll do some design sessions in the practical hours, no actual experiments. Okay, now my phone number, email address are listed in this sheet, and there are essentially 3 books that we will be using. One is Thermal Design by Lee, the first one, and I'll tell you what topics I will cover from the book by Lee. So for that, look at the course content. Now the course content is something that I've directly copied from the courses of study. Okay, so I will not be covered every single one of them, and maybe I will cover some certain things which are not directly present in the courses of study description. Okay, but more or less this is what we are going to do. So it's if you look at the course content, introduction to design, modeling and simulation, then component design, design of heat sink, design of compact heat exchangers, design of heat pipe, and then design of thermoelectric devices. These are the 4 things, right? Design of heat sink, design of compact heat exchangers, design of heat pipe, design of thermoelectric devices. Now we will probably not do design of thermoelectric devices. Okay, what's the reason? The reason is that if we want to cover everything, then we will not have time. Okay, in 42 lectures, in our experience, it's not possible to cover everything. But we'll definitely cover design of heat sink, design of compact heat exchangers, and design of heat pipe. Okay, and all these will be covered from the book by Lee. Okay, so this book by Lee, I think there's one copy available in the library. And then we go to system design, which says design of thermal systems, system identification, description with mathematical modeling. So mathematical modeling also will do. Mathematical modeling means that, okay, you have an actual thermal system for which you write the equations. Okay, so maybe you draw a control volume, show the forces there, show the momentum going in, momentum going out, or maybe the heat going in, the heat going out, the heat loss, all that kind of thing, right? And then you write some maybe momentum balance, mass balance, energy balance. That's what we are calling mathematical modeling. And that we'll do with examples of power plant, refrigeration plant, HVAC systems, etc. Okay, so this will be covered from the book by Jaluria. So Yogesh Jaluria, number 2, that book number 2 there, Yogesh Jaluria. So that book is called Design and Optimization of Thermal Systems. That also copy is available in the library. And for these topics, we'll also use to a very limited extent the book by Stoecker, The Design of Thermal Systems. So this is a 3rd edition book, but this was published in 1985. Okay, so last 40 years there hasn't been any um, edition of this, so I suspect that Professor Stoiker is not active in this field anymore. Uh, but the book is useful to a limited extent for us. Now, after that system design section, we'll go to development of numerical model, mathematical techniques, solution of nonlinear equations, etc. So this means that, okay, you have a system. For that you write the equations, so that's a mathematical modeling. But then from that mathematical modeling, you will have to generate solutions also. Just making a model is not enough. So maybe you will do a mathematical solution, analytical solution, or maybe it's a numerical solution. And that solution will generally involve solution of non-linear equations. So you did a maths course, right, in the previous semester. You did a maths course, right? So you know something about solution of nonlinear equations, and I think you have got some exposure to root finding and things like that also. Okay, so after doing all this, so there is, as I said, there is modeling. There is modeling, and there is also the solutions that we generate for this modeling. And after that, we'll go to optimization. So the course name is thermal design, but actually it's not just thermal design, but also optimization. Optimization of the thermal design, in the sense that for a given system, you can make various designs. So let's say there is some problem of a heat exchanger design, and same problem, okay, one particular problem with given data, given set of two fluids and all that. So I give you the problem, and the same problem I separately give it to you and I separately give it to him, and you sit with books and try to design this. You will definitely not come up with the same solution, right? Not come up with the same design, because design is something where you have to make some assumptions, you have to make some selections, you have to make some design decisions. Those are not going to be the same from one person to another. And out of the three designs that I get, one will be the best and one will be sort of okay, and the third one may not be all that good. Okay. So we can have, even for a given problem, we can have multiple designs. We will have multiple designs. Now, how do you know which one is the best? So for that, you need to use optimization. Now, optimization is typically for a given objective. So for example, we have made a design of a heat exchanger. Maybe you want to have a minimization of cost. Okay, so which in industry, that is often a consideration, that we want to make something which will function well, but it will also cost the minimum, okay, the least cost. Because if it's the world is competitive, and if you have made a product which works but it's also expensive, then it might not sell, or the customer might not buy it, or okay, they may not be satisfied, and all kinds of things. So there can be an objective, for example, minimization of cost. It can also be in some systems, it can be also the maximization of efficiency, or maybe you have a limited space in which you want to keep your product, right? So you want to minimize the volume, okay, and maybe in a particular system you want to make sure that there are some exhaust gases, and you want to make sure that the exhaust gases do not have this level of emittance, okay, emission. So that can be an objective function also, that minimizing the emissions coming out from the system. So there can be various possible objectives that we might have in mind. Depending on the problem, we can decide, okay, for this problem, maybe we are going to look at the minimization of cost. And then we just focus on that. So this last section, which you see in the courses of study, is about optimization. So this optimization is kind of like mathematical and numerical, right? So if you look at this look at this course content, you will understand that it has got a wide range. So one range is designing things like heat exchanger, heat pipe, heat sink. Okay, so design these. Now obviously this is an important thing to do, because in industry, for example, I don't know whether you have any industry experience, but in industry you typically would need, in many industries, heat exchanger, and in some industries, in many industries, you will need heat sinks, and heat pipes are also nowadays quite popular. I don't know whether you know about heat pipes. Anybody knows about heat pipe? No. So you know something about heat sink, right? I mean, at least you have some idea maybe. But you definitely know about heat exchangers, because you must have seen that in courses, right? In undergraduate heat and mass transfer course has a chapter on heat exchangers. And I assume that you've come through GATE examination. So you have also seen that chapter on heat exchangers, and you've done some calculations on maybe LMTD, effectiveness, NTU, things like that. So you have some familiarity with heat exchangers. And you know that heat exchangers are widely used in industry. So you understand from the course content that this is going to be a practical course. Because, okay, if you know something about design of heat exchangers, okay, you have value in industry. If you know something about heat sinks, heat pipes, again, you have value in industry. Okay. So that's one aspect of the course. Then there is modeling and simulation, which I told you in the middle part. Okay, you develop mathematical models and maybe you solve those either analytically or numerically. So that's another aspect of it. And the third aspect is optimization. Now, optimization means, as I told you, subject to some constraints and subject to some objective function, we want to get the best possible design. Okay, want to minimize the cost, so what is the design? Things like that. So optimization again is something which is kind of new for you, at least in thermal engineering. You might have seen optimization in industrial engineering, right? Yes, but in the context of thermal engineering, you might not have seen this. Okay, so this is again something new, and this is again something which is valuable. And there is a lot of diversity in the course, because you see that okay, heat exchangers and all that is one class of problems, but here we will learn something on, for example, the method of Lagrange multiplier, last paragraph in the courses of study, and also we will do something on genetic algorithms. Okay, so this is kind of like very different things. Of course, genetic algorithm can be used, and it's actually used in heat exchanger design. So we'll see that also. So they will come together, but individually seen, heat exchanger design will seem very different from genetic algorithm, learning of genetic algorithm. Okay, there's some topics that we might not again have the time to cover. For example, there's thermal design based on inverse methods, which is also important. Everything listed in the courses of study is important, but we might not have time for everything. If I try to cover everything, then some topics will not be covered in adequate depth, which I don't want. Okay, so some topics we will have to exclude. Right, so already told you about the books. These books, I think one copy each will be available in the library. Then marks distribution. So there will be mid-semester, there will be a major examination, we know that end semester. And see, this is a 302 course, as I told you. So for those 2 hours also, we need to have evaluations. So those evaluations will be assignments, maybe some quiz, etc. Okay. So that the exams mid-semester and end semester together will give you 70 marks. Other things are 30 marks. Okay, now the other thing that you should notice is that we'll be using multiple books, right? Actually, there are some books which are not even listed on maybe genetic algorithm and optimization. I didn't want to list too many books, but these top two are the main. Okay, but there will be other books also. So you don't have one single book using which you can learn the whole course. That's not possible. Okay, the topics are such that that's not possible. So I will say that attending class is important, because if you attend class, then your effort becomes less, because otherwise you have to find each book and read on your own. That's not going to be easy. Okay, and so attendance is important. So there is an attendance policy that I have to state. Institute rules have stated that, but don't go by this. Try to attend 100% of the classes. Okay. Right, so who has come now? Abhinay Kumar, okay. All right, now we'll have some kind of an introduction to the course now. Okay, so this was the course content in this course introduction sheet, but let's look at some example and let's try to get some idea about what we are going to do. So I'll take an example. Okay. So this is a broad thing about design, thermal design. So we will take some overview of the design of a heat exchanger, design of some heat exchanger. Okay. From that, try to understand how this course will go, what we will cover in this course. Okay, so let's say there is a waste heat recovery system. Okay, so your maybe there is some boiler, so this fuel is burnt and there are hot flue gases and the gases are going out. Okay, if the gases are going out, then you are losing heat, correct? Because it's being released to the atmosphere. But heat is a good thing in the sense that you can use that heat to do something else which is of use to you. So imagine a plant where there's some source of gases at high temperature, and that heat contained in the gas, that heat available with the gas, actually gas doesn't contain heat, it contains internal energy. So that energy you want to utilize somehow. Okay, so one possibility is that maybe you can heat water to produce steam. What's the use of producing that steam? Maybe that steam will be used in some downstream process. Okay, you can use that steam. So let's an industry example. So that steam may be used to dry some cloth, dry some fabric, maybe some textile engineering, the textile industry. Okay. So we want to recover waste heat. Now in this example, the flue gases are coming from a diesel generator set. Okay, so you're burning diesel, so there are flue gases. They're going out, you want to exploit that energy. You want to put that energy to good use. So you want to produce steam for use in a laboratory. So what is the requirement of the steam? That's one thing that we have to know. So if you are thinking about this picture, then you will also have to define the amount of steam that you are targeting. That okay, this much steam we need, and at this temperature and pressure of the steam and things like that. And let's say this laboratory which wants to use that steam requires steam at 5 kg per minute, and it requires dry saturated steam, okay, at a pressure of 2 bar. This is just some numbers. I mean, it's just something that we are quoting, just to make the example concrete. It can be something else, no? Maybe 10 kg per minute, maybe not dry saturated steam, maybe superheated, whatever. Okay. Let's say the water temperature. So water has to be heated to steam. So the water, let's say it comes at 10 degrees centigrade. So 10 degrees Celsius. And if we know we know the flow of water, right? And it has to be taken from 10 degrees Celsius to what? 10 degrees Celsius is the inlet temperature of water, and then you get steam at that we'll find out, right? We'll find out. I mean, I don't have the numbers, but it's like you look at 2 bar, what is the dry saturated steam, isn't it? So from that you can calculate the heat transfer that is required, right? And so that's the water side, okay? What about the gas side? Now we are thinking about a heat exchanger which will transfer heat from a hot gas to a colder liquid, which is water, and convert that water to steam, okay? This is the picture. Now the flow rate and temperature of the hot gases exiting from the DG set will be known from the performance data, because you are running the DG set. So you will know at what temperature these hot gases are coming out and what's the mass flow rate of the hot gases, right? This will be known, correct? All right. Now, there are various kinds of heat exchangers possible, that you know, isn't it? From undergraduate and from your preparation for examinations, you kind of know that there are various kinds of heat exchangers possible, okay? So the simplest heat exchanger is like a double pipe heat exchanger, then parallel flow, counter flow, these things you know. Anything else you know about heat exchangers? Like types of heat exchanger? Cross flow is also there. Shell and tube heat exchangers. So shell and tube is one possibility. There are many other kinds of heat exchangers. We'll be able to cover a limited range in this course, because again, if you want to study heat exchangers in detail, then again you have to study in detail for a full semester. That's not the purpose in this course. The purpose here is to introduce you to some heat exchangers and broadly how to design a heat exchanger. Okay. Now, we have to choose the type of heat exchanger. So we know that this is okay, flue gases. We want to convert water to steam. Now what? Now the point is that we have to choose the type of heat exchanger. So one possibility is that we choose a tube fin heat exchanger. Okay, so I'll tell you what is a tube fin heat exchanger. Now also, how do you choose a tube fin heat exchanger? Who tells you that you shouldn't choose something else, right? Some other type. There are plate fin heat exchangers. There are other kinds of heat exchangers, various other kinds of heat exchangers. So plate heat exchangers, plate fin heat exchangers, shell and tube heat exchangers, and many other kinds of heat exchangers. Why do you choose the tube fin heat exchanger? Now, this choice comes partially from experience and from industrial practice. So if you are an engineer working in an industry, you kind of know that for this sort of application, tube fin heat exchanger works out well. Okay, there are many instances of people using it. Also, a tube fin heat exchanger is good for gas to liquid heat transfer. This is going to be gas to liquid. No, it's not liquid to liquid. So experience is a major thing. So that's why I have underlined this word, that okay, so this is done based on experience, but it's also based on many other constraints. For example, it also depends on the type of fluids that you have, okay, and their fouling potential and cleanability. So which fluid in general we think about before we choose the type of heat exchanger? We think about what kind of fluid will be used and how much fouling it can do. When you start with a new heat exchanger, I mean you've designed it and just made it, then it actually when you just made that heat exchanger, when it's a new heat exchanger, everything's fine and everything's clean and all that. But you also have to keep in mind that you will be using it for several years, right? And then there will be deposits on this, so there will be fouling. And what does this word mean? Cleanability. Cleanability means, you know, how much access you have. Okay, then let's say there are tubes. Can you access the tubes and inside of the tubes, and how difficult it is, and um, will it be possible to clean it properly? Things like that. There are also other considerations of pressure drop and what happens if there is a leakage. You know, if you have a corrosive liquid and if there is a leakage, then there is a problem. Pressure drop. Pressure drop is an important thing. So you will know from this course, and you probably already know, that typically if you want to increase the heat transfer, then the pressure drop also, what happens to the pressure drop? Pressure drop also increases. So it comes at the, if you want to increase the heat transfer, it typically comes with a cost. Okay, so the pressure drop also increases, because the logic is like this, that let's say you flow fluid over this. So if you increase the fluid velocity, heat transfer will increase. But if you increase velocity, pressure drop typically increases, isn't it? Remember that for flow in a tube, pressure drop is like FLV squared by 2 dg. You all know this relationship, right? So V squared, right? So if you increase the velocity, the pressure drop will increase with the square of the velocity. So increasing velocity will give you increased heat transfer, but there will be greater pressure drop also. So we have to, sometimes we cannot afford the pressure drop, because the pressure drop costs money. Why? If I say pressure drop costs money, what does it mean? You need to pump, no? So typically there is some pumping involved. The fluids are moving through the heat exchanger. So pumping is involved. Pumping the fluids, like if there's a gas, maybe some blower. If there's a liquid, there's a pump. Things like that, isn't it? So that costs money. Yes. That's part of the recurring cost, isn't it? So it's obviously you don't want a lot of pressure drop. So in a lot of heat exchanger design, you will see that the pressure drop is limited, that okay, pressure drop should not be above this. So let's say you make a design and then Dhananjay makes another design, and you are Abhay, right? Sorry. Abhinay. Okay. So you all make different designs, and one has a lot of pressure drop, then that probably we have to reject. That might not work. Okay. Right. So this is a constraint, right? The objective of making this heat exchanger can be, okay, reducing cost, increasing efficiency, whatever, but pressure drop also. So there are constraints. We have some objectives, we have some constraints. Limit the pressure drop can be one. Okay, so tube fin heat exchanger is good for gas to liquid, that sort of thing. and it also helps minimize the pressure drop on the gas side. Now we'll just quickly look at what a tube fin heat exchanger is like. Okay, so this is the tube fin heat exchanger. Tube fin heat exchanger. It's also called finned tube heat exchanger. So just take 30 seconds to look at this. So what do you see? You see, let's say this tube, and what are these? These are fins. So these are circular fins. This is something similar, but this is like plate fins. Now this fin, this one, is obviously not like this, appearance-wise. This is a circular fin, but this is also a fin, similar. And these are also fins, but they're here. The tubes are not circular. Okay? We will see, like later on, we'll understand these better. And what this sentence here says is that tube fin heat exchangers are good for heat exchange between gases and liquids, and they have been used for many years. And these are used in air conditioning, refrigerator, and automotive industries. Okay, so this is a good thing. So we will choose this, and we will let what will flow. I mean, if we choose something like this for our example, the example that we're doing, where will the gas flow? Where will the liquid flow? What do you think?
In tube, water from outside gases because we want to increase heat transfer from the gases to water. So the surface, so the fins area will be area increasing.
Correct. That is correct. See, the reason we flow gas on the outside, so his answer is correct, is because gases typically give you lower values of heat transfer coefficient. Okay, so whatever is weaker, whichever side is weaker, you want to help, obviously, and you add fins on the outside of the tubes because the gas will flow outside of the tubes. Okay. Now, why? What is the logic behind all this? So there is for the flow in a tube. This is a tube, right? So this is a tube wall, and there is some fluid which is flowing inside this, and there is some heat transfer coefficient HI, okay, some heat transfer coefficient HI for the heat transfer from the gas to the wall, right? There is HI. But there will be some gas flowing outside. I'm not drawing the fin for simplicity. Okay. Just say that there is some heat transfer coefficient outside. Okay. There are two heat transfer coefficients, you know this, and they are combined in some way. Isn't it? What is this combination? You've seen this in an undergraduate. There is something called an U. There's something called an U. What is U? Overall heat transfer coefficient, which will be like a combination of HI and HO, right? So what's the relation between U and HI and HO, if you can guide me on that? So you need to revise your fundamentals of fluid mechanics and heat transfer, and of course thermodynamics also, for this course, because as I told you, this is an applied course in which these fundamentals will also be required, isn't it? Here we will not have enough time to actually go through all fundamentals, isn't it? So you have, all of you I'm sure have you got some undergraduate heat transfer book with you? Not in class, I don't mean in class, but you have with you, right? Some undergraduate text, heat transfer text. Okay, so what's the connection between U and HI and HO? Okay, so we'll make a further simplification. We'll say that all areas are the same. If this is a thin walled tube, then the inside area and the outside area will be approximately the same, right? Then mu is 1 by U. Okay. Right? So this is HiHO and this is Hi plus HO. So U is HiHO divided by Hi plus HO. Okay? And we understand by studying this that if you have this situation, then U will be dominated by the smaller of the heat transfer coefficients, isn't it? Out of Hi and HO, one is smaller obviously, the other is larger, and U is limited by the smaller value, isn't it? So if you have a gas giving you a small value of H, then U will be closer to that value of the H, isn't it? That smaller value, isn't it? So that becomes a problem. So to help that situation, we built fins. We built fins on the side where the gas flows, because on that side the heat transfer coefficient is smaller, right? So that's why we have these areas. Okay, so more about fin tube heat exchanger after actually not immediately, after quite a few classes. Okay, so we will as we go along, we'll look at heat sink and then we go to heat exchanger. Okay, after some initial classes, after some initial introduction to the class. All right, now let's go back to what we were saying. So I said that the tube fin heat exchanger is good for gas liquid transfer, minimizes the pressure drop. But okay, now next job is, okay, you choose some fin tube, we choose some tube diameter, some height of the fin, some thickness of the fin, things like that. So this is typically done based on quote unquote good industrial practices. Okay, so some previous experience, this thing works and all that. So suppose we choose tubes of diameter 16 mm. So this is if we say base diameter of 16 mm, it might mean inner diameter of 14 mm. Okay. And then also we have integral fins on the outside with 2 mm height, 2 mm height spaced on the tube with a pitch of 4 mm. Okay. What is pitch? Pitch means that, alright, so pitch will mean, see, between this fin and the next fin, the distance, we'll call that pitch. Okay. And we also have, so apart from this, so on tubes we have fins, right? So that much we have understood. We have chosen the tube diameter, we have also chosen the fin size and fin pitch. These things we have done based on some experience. Somebody has told us that this has worked and our previous experience and all. Okay, but you still have to place the tubes with the fins on them in a broader setup, right? So that setup is this duct. So this is a duct through which the hot gases flow. This is the flue gas from the DG set, right? And they will flow like this. So the tubes here, this is a particular arrangement that I have got. The tubes give you a staggered arrangement in this case. So you probably know, you must have studied in heat transfer in undergraduate. There can be, if you have a tube array, tube bank you've studied? Tube, no? What's it? Tube bank, no. Okay. So some books have this on undergraduate level also. So there can be arrangement of tubes that are inline. So inline tubes are these are inline. Okay. And what is staggered? Staggered is this is staggered. Like this. This is staggered. Like what you see here, this is a staggered arrangement. Not inline. All right. Now, why do we give a staggered arrangement? Actually, it has some advantage, like see, the gas comes here. In inline arrangement, there is this chance that some gas will just flow like this, straight path, without resistance. Whereas in staggered arrangement, this gas also has to encounter a tube. Correct? Because here there can be a tendency of the gas bypassing the tubes. Here bypass is more difficult. It has to experience the presence of a tube. So that's why staggered arrangement is sometimes preferred. And we can have this kind of an arrangement. So if you have this kind of arrangement, then we also have to think about the pitch of tubes in the transverse, T for transverse direction, and also pitch in the longitudinal direction. Okay, so we talked about pitch of fins few minutes back, but there will be pitch between tubes also. Two pitches, transverse and longitudinal. So then the question is that again you need values of ST and SL. So we'll close in 1 or 2 minutes. So you need the values of ST and SL, and ST and SL in this example we choose as 32 mm and 30 mm. Again, how do we choose this ST and SL? Based on experience, right? The other thing is that we will have to also choose the size of the duct. Which duct? This is this duct. Okay. So you've chosen tube diameter, pitch dimensions, etc. But this also is important, right? because the total gas flow comes through this. So you can have this many tubes in a large duct or a small duct. That will change the velocity of the gas, isn't it? And if you change the velocity of the gas, the heat transfer from the gas to the water will also change because of velocity. Right, since there is, I think, some people waiting outside, so we'll stop here. Okay, thank you.